What is a compiler? A compiler translates some programming language, C++ for example, to another, generally lower level one, for example assembly. Lower level meaning little or no abstraction from the instructions the processor can execute directly. How do they work? The structure of a compiler can look like this. Can be done in various other ways, but we will stick to this simple one. First, we have the compiler front end, which generates an intermediate representation of the source code. The intermediate representation is much easier to work with than the original code. The front end is often implemented with two components, a lexer and a parser. We'll see how they work later. In the middle end, the compiler works on this intermediate representation. For example, the code might be optimized, warnings might be generated. We will not go into that. In the back end, this intermediate representation is used to generate the output code. The lexer takes the source code as an input and transforms it into tokens. Tokens are meaningful chunks, like words in a language. For example, this code might be broken into these tokens. The 42 is one meaningful chunk and becomes one token. Same goes for the variable, the equals sign, and the multiplication sign. So a token has a type like integer, variable, and so on. Let's see how this can be implemented. I'm gonna show you some source code, so that can be a bit overwhelming. That's why I'm gonna try to point out what is really relevant. Try to ignore the other stuff. So let's start with that. Here we got some tokens that some hypothetical programming language might have. If, else, false, true, for, return, while. It's not important that you know exactly what they mean. Important is that these are meaningful chunks in the language. So it's not just FOR, it's for, and that has one meaning. Now, if we start using the lexer, it's initialized with some string. So for example, ABC plus 3, or something like that. And it's also initialized with some empty vector of tokens, which is a list or array list in Java, I don't know. Now, if we do the lexing, then what we do is we scan one token after another, and that means going over the characters in the string one after another. Now, I'm gonna show you this main method of the lexer. This is this scan token method, which is called in this while loop until we reach the end. So the scan token method takes a character from the string. The advanced method wraps that nicely. And then we have a giant switch case here, and we filter out some very simple tokens which consist of one character. And they are just detected right away, and then we add the token to the token vector, which is the result of the lexing operation. That's quite simple. Then here, that's interesting. We have if the character is a white space, then we just ignore it. Also, we do line number counting, which is important for error reporting. And then we have some 2-character tokens, For example, if you have two equal signs after another for equality comparison in a lot of languages, then we have to first check the first character, and then if there's another equal sign, then this token appeared. But yeah, not gonna go too deep into that. Then we have got some more cases which are, oh, I deleted that, which are a bit more interesting. So we check if it's a number, or to say better, if it's a digit, then we start looking for further digits to lex a number token. And the same is for characters. I think the interesting, I'm just trying to show one. More interesting is probably the one for the identifier. So I'm going to take a look at that one, which is here. And here you see we go through the string as long as we meet other characters. And then we take the substring from the whole input for this token, and then we add this in the end. And then now, that's important, we check if this actually was a keyword of the language. For example, for, while, which we saw in the beginning here. That means we have, yeah, a lot of tokens to work with further down the compiler. Now let's take a look at some parser theory. The parser takes the tokens the lexer produced and creates an intermediate representation. This is usually some kind of tree. Let's see an example. Here we have the tokens the lexer produced, some variable, an equal sign, an integer, a multiplication sign, and another integer. The parser then produces this tree. The top level node is of type assignment. The first child is the value of the assignment. The second child is the variable it gets assigned to. The value, in this case, is a binary operation node with the two integers as children. How this tree gets created is the magic of the parser. There are many different ways on how to do this. We will take a quick look at a parsing technique called recursive descent. To understand how any parser works, we need to understand what a formal grammar is in the context of parsers. A grammar is a set of rules that describe how a valid program looks like. For example, this rule describes how an if statement in some hypothetical programming language looks like. It says that an if statement must contain first a literal if, followed by an opening bracket. Then there must be an expression. What is an expression is described by another rule. Then we have a closing bracket. And then we have the body. What a body is described by another rule. So you see that these rules can reference each other and have a tree-like structure themselves. Now back to the recursive descent parser. He, as the name says, recursively applies this set of rules to the tokens from the lexer. For each rule, the parser has a method or subroutine. For example, the subroutine for this if statement rule here could look like this. To understand the naming conventions
and recursive descent parsers in general, one must imagine a parser as if he eats through the tokens one after another. I think this is a good picture to keep in mind. First, he eats the if, then the left bracket, then he calls another subroutine to parse the expression. This returns an expression node. Then he eats the right bracket, and then he parses the body. In the end, he returns the result of this parsing operation, an if statement which has two child nodes, the condition and the body. Remember, the goal of the parser is to produce a tree. Since the translation of grammar rules into code like this is so predictable, we can use an automatic parser generator that creates this code for us. But there are good reasons to write your own parser. For example, error reporting can be done a lot better by using a handwritten parser. That's why most parsers for big languages like Java or Python are handwritten.
Again, let's take a look at some source code. Now I used a library to auto-generate the parsing code. That makes it pretty hard to read through, but I think I'm still gonna show this code just so you see how a compiler can be implemented. So just like in the lex method, here in the parser we have a parse method. In the first line, what we do is we auto-generate the parsing code from some grammar rules that we defined before. Here we have these grammar rules. These 4 grammar rules are enough to parse some basic math. Maybe I'm gonna show one rule, this rule here, that is parses a primary expression. And a primary expression in my simple compiler here is either a number, here a number, so a token, number token, or it's first a left parent token, followed by an expression, which can be anything like 1 plus 2 or whatever, followed by the right parent token. Now there's other rules that express multiplication, addition, stuff like that. And yeah, these rules are used to auto-generate the parsing code in the way that I showed before. And then what this method does is just it actually passes the tokens from the lexer to this auto-generated parser, and then if this is if we can successfully parse these tokens, we return some value here, and that is in our case a tree. I could show the data structure, but I think that's going too far. Yeah, that's for the parser code. It's gonna be a little more interesting in the code generation code. We can see more stuff there. Now back to some theory.
Now that we've covered the front end, let's see how the back end can use the intermediate representation to output lower level code. To do that, it traverses the tree in execution order and outputs lower level instructions that the target architecture can understand. This means what exactly the back end has to do depends heavily on the processor or virtual machine or on whatever the code should run on. We can say that is the target of the compiler. For the sake of simplicity, we'll say that our target architecture just understands very few commands and operates on a stack. A stack is a data structure, a way of storing data where you can add data on top of it and only read the data at the top. Imagine a stack of paper where you can only read the top paper. So in my little drawing, it's only possible to read the number 2 and put, for example, a 3 on top here. In this little example target, we will support very few operations, like loading a constant, meaning putting something on top of the stack, adding, meaning adding the upper 2 stack entries and putting the result back on the stack, multiplication, and terminating all operations. In this case, the top entry of the stack is the result of the whole calculation. A real CPU has of course a lot more operations and is usually register based. Meaning that you have, for example, 64 sheets of paper next to each other that you can always access. And there are operations like send some stuff to the GPU and then further to the monitor, or load something from the network. Let's see an example how a backend might generate code for such a target architecture. Let's say the source code looks like this. Simple 2 times 3 plus 4. Then the front end produced this intermediate representation. Now the back end will traverse the tree in execution order and output these comments. Let's go over them one by one. We start traversing the tree, starting with the top level node. Then we go to this binary operation, but we first have to evaluate left and right node to perform this operation. That's why we go deeper in the tree. Now first we evaluate the left node, in this case an integer with the value 4. That's simple, we just push 4 onto the stack. Okay, then we go to the right node of this binary operation. See, that's a multiplication. Again, we can't evaluate it directly, we first have to evaluate the children. Go to the left child, that's an integer, 2, simply. Oh, I did that actually wrong. This is a 2. That's a 3. Okay, we push the 2 on the stack. We see the comment here. Then we go to the 3 and push that on the stack. Now that we've done that, we go back up the tree. Then we meet this multiplication operation where we have evaluated all the children. Now we can actually execute the multiplication and put this command to the commands that we have to execute. Same goes with the addition. Then we have seen the whole tree, we terminate. Let's see some example execution. So first we push the 4 onto the stack. Then we push the 2 on top. Then we push a 3 on top. Now we have all the relevant data that we need on the stack. Then we have a multiplication command, and that means we multiply the top 2 entries of the stack. That results in a 6. Then we add those 2 together, which results in a 10. And then we have a termination command, and we are done with our calculations, and you see that we did the math correctly. Again, let's take a look at some real C++ code to see how this can be implemented.
So in our case, the backend just consists out of a code generation that spits out these simple operations that some target architecture can understand. Now let's take a look. So the code generation similar to the lex method, the lexer, and the parse method. The parser has this generate method which spits out a chunk. What is a chunk? A chunk is just some data structure to collect these simple operations in a succession, one after another. Then here we start to visit the tree. How this exactly works, I think, is out of the scope of this video, but I'm gonna show the visit of one of the nodes. So here we get to this method if while visiting the tree we encounter a binary node. Binary node, I mean plus, multiplication, stuff like that. So just as we discussed in the theory section, we have to first evaluate the children, and that happens here. First we evaluate the left child and then we evaluate the right child. Now then we have actually interesting stuff happening here, because depending on the operation, if it's either plus or minus or whatever, we put an operation into the chunk, and that happens in this line here. So we append the simple multiply operation in case that we encountered a binary node which does multiplication in a tree walk. This part here is just to get back to this. We always propagate the line number in case that we encounter an error at some point in the whole process. Then we can inform the user in what line the error happened. Yeah, then maybe one other of these rules. If we encounter a very simple node, a node with a literal expression, then since we just do simple math, then what we do is we append a constant, and that means the simple push the constant to the stack operation that is here formulated a little bit different. So that's all very dry theory. Let's see this whole stuff working together. So let's take a look at our main method. So this ties this all together. First, we have the lexer. First, we have the input. I don't know, we do a multiplication here as well, and I don't know, divide this by 3 and times 35, I don't know, something that I can't calculate in my head. This input is forwarded to the lexer. So we initialize the lexer with this input, and then we actually run the lexing operation, this lex method, which we saw before. Then we just print that to see if it worked. After that, we do the parse operation. After that, we actually print this tree in some human readable format just to see if that worked. And then we have the code generation, generate code, and same as parse and lexer, we actually in this method we print out the chunk just to see that everything worked correctly. In the end, we execute this code. Maybe I'm gonna just quickly show that as well. Just the core of the virtual machine is this for loop which operates forever, and we have a giant switch case here, which makes this quite fast. And here, so for example, if we encounter this up constant here, which means that put something on the stack, then what we do is we read the constant, which wraps this nicely, and then we put this constant on the stack. So just as I said before. Or maybe here we have a multiply operation this, in that case, yeah, we have some fancy. In that case, we have some fancy template programming here, but I think that is still somewhat readable. So in that case, yeah, in that case, we get the top two values from the stack. So first here, we take this one from the stack, then value B, and then we take another one from the stack, and then we apply this function, the function that got passed into this method here onto these two values A and B, and we actually immediately push back the result. Yeah, just quickly showed here the virtual machine just to show the whole thing. And now, yeah, let's see how this works. I didn't lie to you. Yeah, I think, yeah, we can build that first. Takes a while. Then we have our executable here and execute that one. And as you can see, it worked. The result of our, oh, no, it didn't work. We forget to save the, we actually forgot to save the new, so you saw, at first the math was 10 plus 20 plus 30 and it calculated it correctly. The result was 60. Now just save that file and build that again. And yeah, this time the result is 1780. I don't know if that's correct. I'm too lazy to check that now. Yeah, that was my video on compilers. I hope you took something home. If you're interested in compilers, I can really recommend the Crafting Interpreters book, written by some Google dude that really shows all that stuff in greater detail, better explained than here. Can really recommend that.